One of the most overall detectable physicists, Michio Kaku, has talked about his assessment concerning this issue. Kaku, known for his astounding contributions to the fields of actual science, has as of late recognized that the James Webb Space Telescope, JWST, has seen 6 enormous, endless structures that professionals once thought demonstrated incapable of existing. These exposures have the potential to open up new perspectives on how we may interpret the universe. It is, therefore, both spellbinding and worth looking out for these developments. Kaku is a noteworthy figure in the scientific field, a physicist of American and Japanese heritage. He is viewed as a specialist in both regular exploratory physical science and quantum mechanics. Unlike some more moderate and skeptical analysts, Kaku doesn't belong to that group and has been open to the shocking later revelations of the James Webb Space Telescope mission. We are fortunate that this recognized expert has decided to end his silence and offer straightforwardly what can no longer be denied. The enthusiasm and practically comprehensive tone of the well-known physicist are evident in his remarks on the revelations made by the James Webb Space Telescope. He suggests that these discoveries have been the part that has invigorated his interest. We ought to examine the repercussions of Michio Kaku's revelation of these 6 enormous, tremendous systems. Kaku is a scientist who has consistently had the ability to consider new hypotheses throughout his life. He appreciates that Einstein's theories of relativity and Newton's laws are insufficient to grasp the full, multifaceted design of the universe. Kaku understands that the exposures of the new telescope could significantly improve the scientific field, notwithstanding the fact that many of his peers have not been able to embrace this view. This has caused concern and nervousness among both supporters and critics of quantum mechanics. However, this certified understanding brings out laughter from Kaku. The JWST has uncovered the discovery of 6 colossal universes dating back to the earliest periods of the universe. Each of these huge systems contains more stars than our own, despite forming only a brief time after the Big Bang. The group of cosmologists who made the discovery has named these astonishing systems universe breakers, as their reality would change our entire understanding of the universe. Something here no longer fits with the theory of the Big Bang. The Big Bang theory tells us that the universe was a turbulent place following the beginning event. The first strong objects took several hundred million years to form, and it required endless additional years for these objects to achieve a sufficient density to produce light. The development of complex designs like systems was supposed to happen much later. Some of the newly discovered systems exceed the size of the Milky Way, and their massive magnificence suggests that they were possibly forming many new stars each year, while our own galaxy forms stars only sporadically. It remains disputed precisely when the first universe formed. Scientists have not been able to decide this until recently. The one thing that is clear is that initially, there could have been just single stars or alternatively gatherings of stars that eventually came together to form consistently larger structures, ultimately leading to the evolution of dwarf galaxies, which went through mergers and continually developed as shown by previous theories. According to these theories, very advanced and massive systems could not have existed at that time, which raises the question of whether the universe is actually older than previously acknowledged or whether complex large-scale structures existed much earlier than anticipated. This current situation is challenging for traditional science, which still struggles with this model. Additionally, some areas of physics have firmly dismissed this discovery, highlighting potential errors in the age calculations. Kaku, aware of this, had this to say: "There are many instances of old and misleading theories that stubbornly persist due to the prominence of certain researchers. Many of these speculations were ultimately disproven when fundamental examination revealed their distortions. Consequently, the essential work in any science, particularly in physics, rests with the experimentalists who maintain the validity of examination through precise truth. On Earth, we have essentially no data on the actual origin marks of the universe. The Big Bang theory was laid out in 1927 based on observations of the universe's expansion. This information led to the conclusion that the universe began from a single point and has been expanding since then. At the time, it was hard for people and scientists to imagine a universe with a beginning and an end. The possibility of a universe that had always existed and was infinite in time was beyond human imagination. In fact, even today scientists still face difficulties in understanding it. However, it is crucial to reconsider these possibilities. These new insights don't fit with what scientists have relied upon for years in the theory of how things came to be. Nevertheless, science has repeatedly shown that reassessment and openness to significant ideas are vital parts of the scientific process, just as much as the confirmation of specific hypotheses and observations. When Einstein was a young scientist, he believed planets were fixed in the universe and that these specific plans involved a defined space. However, we now understand that everything in the universe is moving. Planets orbit stars, stars move within their galaxies at various rates, and entire galaxies move rapidly through space, the ultimate fate of which we still can't predict today. Analysts are challenged to accept uncomfortable revelations, and it is understood that theories are not just hypotheses or significant insights until they are thoroughly tested or confirmed by conclusive observations. The possibility of the Big Bang emerged from the confirmation that galaxies are moving away from each other, and this distance is proportional to their separation from Earth. This observation, known as Hubble's law, suggested that the universe has been expanding for a long time. Additional evidence, like cosmic microwave background radiation and the redshift of light from distant galaxies, as well as other cosmic patterns, seems to support this theory. However, it is important to remember that those who once believed the Earth was flat and that the Sun revolved around us also had similar kinds of evidence for their doubts until events or technological advancements provided a clearer and more accurate picture. Presently, we are seeing a similar situation. Scientists expected the JWST to validate intuitions about the Big Bang. However, instead, they have found 6 systems that seem to be too large for their age. This reminds us that science is always evolving and experts must remain open to new discoveries and reevaluate existing theories based on available evidence. Scientists use redshift as a tool to determine specific measurements in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as the light source and the observer move relative to one another. To understand this, imagine watching a car coming toward you. As it gets closer, you hear the engine getting louder. However, once the car passes you or moves away, the sound changes. This is because the sound changes as the car moves. The same is true for light. When a light source, like a distant star, moves toward us, the light we see shifts toward the blue end of the spectrum. On the other hand, when the light source moves away, the light shifts toward red or tints. This phenomenon is known as redshift. Physicists have converted redshift values into speeds and distances for assessing quantities in the study of the universe. At any rate, it is significant to note that small errors in these calculations could have enormous implications. The measurement techniques used in the past are now under review, and the results that scientists will arrive at regarding the most recent discoveries related to our universe are exciting. It is important to consider whether these results are truly based on redshift mistakes or whether some scientists are simply denying the facts. This is a question that requires serious appraisal and a careful review of the data and methods used in the investigation. As scientific inquiry progresses, discoveries made by instruments like the James Webb Space Telescope frequently challenge our assumptions about the universe. The ongoing discovery of 6 massive galaxies, dating back to the beginning of the universe, is one such example. These galaxies, which defy the standard theory of galaxy formation, raise critical questions about the timeline and processes involved in the development of large-scale structures. The James Webb Space Telescope, a replacement for the Hubble Space Telescope, is equipped with cutting-edge technologies that allow it to peer deeper into space with striking clarity. Its ability to detect light from the farthest reaches of the universe provides astronomers with a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and massive galaxies challenges existing models that predicted such large structures should have formed much later in the universe's history. The implications of these discoveries extend beyond astronomy and into the realm of fundamental physics, compelling scientists to reconsider established theories about the early universe. These revelations also highlight the importance of remaining open to revolutionary ideas and adjusting our understanding based on experimental evidence. Kaku has emphasized the crucial role of scientific validation in shaping our view of the universe, pointing out that theories must constantly evolve to accommodate new data. The debate sparked by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, There are supporters who argue that the discovery of early massive galaxies suggests a longer timeline for cosmic evolution than previously thought. This perspective challenges the traditional view that galaxies evolve slowly over billions of years through mergers and the gradual development of smaller objects. On the other hand, skeptics caution against quickly discarding established models based on limited observational data. They advocate for a more cautious approach, suggesting that anomalies in data interpretation or measurement errors could explain the surprising discoveries. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a significant role in these critical examinations. As galaxies move away from Earth, the light they emit shifts toward longer wavelengths, a phenomenon known as redshift. By measuring the degree of redshift in a galaxy's light spectrum, astronomers can infer its distance from Earth and its speed relative to our own galaxy. This data is essential for developing models of cosmic evolution and understanding the expansion of the universe. However, redshift measurements also carry inherent uncertainties. Small errors in determining the redshift of distant galaxies could lead to significant misinterpretations of their age, size, and other characteristics. As such, the discovery of these 6 massive galaxies prompts a reassessment of how astronomers measure and interpret redshift data, potentially leading to new insights into the early history of the universe. As the James Webb Space Telescope, JWST, continues to provide groundbreaking insights into the universe, scientists are grappling with the implications of its findings. The discovery of 6 massive galaxies formed shortly after the Big Bang raises profound questions about the traditional models of cosmic evolution. These galaxies challenge our previous understanding of the timeline and mechanics of galaxy formation, suggesting that large-scale structures may have formed much earlier than previously believed. This revelation pushes the boundaries of astrophysical theory, compelling scientists to rethink existing paradigms about the universe's infancy. One of the primary theories that is being re-examined is the rate at which galaxies evolve. According to earlier models, galaxies were expected to grow over billions of years through a gradual process of mergers and accretion. Smaller objects would combine over time to form larger, more complex structures. This model assumed that the conditions necessary for the formation of massive galaxies would take longer to develop. However, the JWST's detection of these 6 early galaxies, which are significantly more massive than expected for their age, suggests that galaxy formation was far more rapid and efficient in the early universe than originally thought. These findings challenge the conventional wisdom about the hierarchical structure of the universe, which posits that large galaxies gradually evolve through a series of mergers and interactions. The idea that such large, mature systems could have formed so early raises the question of whether there might have been other mechanisms at play in the early universe. Some scientists have suggested that the conditions following the Big Bang may have been more conducive to the rapid formation of large-scale structures. This would mean that the universe might have experienced a much more turbulent and dynamic early phase than our models currently account for. Another potential implication of this discovery is that it could lead to a re-evaluation of our understanding of dark matter and dark energy. These mysterious components of the universe play a crucial role in the formation and behavior of galaxies. Dark matter, which does not emit light but exerts gravitational influence, is thought to have been a key ingredient in the formation of early galaxies. The massive galaxies detected by the JWST could provide valuable insights into how dark matter interacted with normal matter in the early universe, influencing the speed and scale of galaxy formation. Dark energy, which is responsible for the accelerated expansion of the universe, could also play a role in how galaxies evolve. The relationship between dark energy and the formation of large structures is still not fully understood, and discoveries like those made by the JWST may provide important clues. By studying the earliest galaxies and their properties, scientists may be able to uncover new information about the forces that shaped the universe's expansion and the development of its large-scale structure. Moreover, the detection of these early massive galaxies could lead to a broader understanding of the environmental conditions in the early universe. The presence of such large galaxies so soon after the Big Bang implies that the gas and dust from which these galaxies formed must have been more concentrated or more readily available than previously thought. This could suggest that star formation and the process of galaxy assembly were occurring at a much faster pace than previously understood. These findings may point to a higher degree of initial density in the universe or a different mechanism for how matter accumulated and condensed into galaxies. The ongoing research inspired by the JWST's discoveries could also have significant implications for our understanding of cosmic inflation, the theory that the universe expanded exponentially in the moments following the Big Bang. If galaxies formed more quickly than expected, it could indicate that the early universe underwent more rapid and chaotic inflation, allowing matter to clump together and form large structures earlier in its history. This would require a rethinking of the models that explain the early stages of the universe's expansion, potentially revising key assumptions about the speed and nature of cosmic inflation. In the coming years, astronomers and physicists will likely continue to study these early galaxies in greater detail. The data collected by the JWST will provide a wealth of information that could help resolve some of the most fundamental questions in cosmology. How did the first galaxies form? What role did dark matter and dark energy play in their creation? How did these early galaxies evolve into the structures we see today? These questions are just the beginning, and the answers could reshape our entire understanding of the universe's history and its eventual fate. The James Webb Space Telescope's ability to peer deeper into space than any previous instrument has opened up a new frontier in astrophysics. As we continue to explore the universe's early moments, we are not only gaining new knowledge about the cosmos, but also challenging and refining the theories that have long defined our understanding of the universe. The discoveries made by the JWST represent just the beginning of what is sure to be an exciting era of astronomical research, one that promises to reveal even more about the vast and mysterious universe in which we live.